Hey there, and welcome. Have you ever looked at a really complex situation with things being pulled in all these different directions and just wondered, okay, what's actually going to happen here? Well, today that's exactly what we're going to figure out, but in the world of physics. We're going to take a bunch of competing forces and find the one single force that tells the whole story. Let's jump into our puzzle.
So take a look at this. You've got this single point, we'll call it O, and it's getting yanked in three different directions by three different forces. It's a classic engineering problem, right? The big question is, where does that point actually go? It's definitely not as simple as it looks, and honestly, that's what makes this so cool.
So here's our mission, plain and simple. We have an 800 Newton force pulling up and right, a 424 Newton force pulling down and left, and a 408 Newton force pulling down and right. Our job is to find one single force that does the exact same thing as all three of these combined. In physics, we call that the resultant force. Now I know what you might be thinking. Why don't we just add the numbers? 800 plus 424 plus 48, right? But if we did that, we'd get this huge number and it wouldn't tell us a thing about the final direction, which is just as important as the strength. So why doesn't that work?
It's because forces are what we call vectors. And that just means they have two critical pieces of information, their strength, or magnitude, and, you guessed it, their direction. Since they're not all pulling in a nice, neat line, we can't just add them up. We need a way smarter strategy.
And that strategy is a classic for a reason. Divide and conquer. Instead of wrestling with these awkward diagonal forces, we're going to do something really clever. We're going to break each one down into two super simple parts. One that pulls purely left or right, and another that pulls purely up or down. This is the secret sauce to solving the whole thing.
These simple parts are called components. And honestly, the best way to think about them is as the shadows of the force. Imagine you're holding a flashlight directly above the arrow. The shadow it casts on the ground? That's your horizontal or X component. Now shine a light from the side. The shadow on the wall behind it? That's your vertical Y component. Simple, right?
All right, let's get our hands dirty. We're going to go through this step by step, calculating those horizontal and vertical components for each of our three forces, and we'll keep everything nice and organized in a little table as we go.
And here's the game plan we'll use for each one. It's a simple three-step recipe. First, we look at those little triangles the diagram gives us for each force. Second, we use those triangle sides to figure out the ratio, basically, how much of the force is horizontal versus vertical. And third, we just multiply the total force by those ratios. That's it. Let's do it.
Let's start with the big one, the 800 Newton force. If you look at the diagram, it shows us that its direction is defined by a triangle that's 800 millimeters wide and 600 millimeters tall. Using a little bit of Pythagoras, we can find that the long side of that triangle, the hypotenuse, is an even 1,000 millimeters.
Okay, time to apply our ratio method. To get the horizontal part, we take our total force, 800 newtons, and multiply it by the horizontal side over the long side. So 800 over 1,000. That gives us a pull of 640 newtons to the right, which we'll call positive. For the vertical part, it's 800 newtons times the vertical ratio, 600 over 1,000, which gives us 480 newtons. And since it's pulling up, that's positive too. Let's pop those into our table. 1 down, 2 to go. We're just going to rinse and repeat for the 424 Newton force. The triangle for this one is 560 wide and 900 tall. Now this is really important. Pay attention to the direction. It's pulling left and down, so both of our components are going to be negative.
Okay, let's run the numbers. The hypotenuse for this triangle works out to 1060. So the horizontal pull is 424 times 560 over 1060. That's 224 newtons. And because it's going left, we make it negative. The vertical pull is 424 times 900 over 1060, which is 360 newtons. It's pulling down, so that's also negative. Let's add them to the table.
And here we are, the final force, 408 newtons pulling right and down. Its triangle is 480 by 900, so we've got a mix this time. The horizontal right part will be positive, but the vertical down part will be negative. You're getting the hang of this now, I can feel it.
For this last one, a quick calculation gives us a horizontal component of positive 192 newtons and a vertical component of negative 360 newtons. And look at that, our table is full. This is perfect. We've successfully divided this complex, messy problem into simple, easy-to-manage pieces.
So, the divide part is officially done. Now it's time to conquer. And this is the easy part, I promise. Since all our horizontal bits are just pulling left or right, we can just add them up. And we can do the exact same thing for all the vertical bits. Let's tackle the horizontals. We've got a plus 640, a minus 224, and a plus 192. Add all that together, and the grand total is a positive 608 newtons. What that means is, after all that tugging left and right, the net result is a single pull of 608 newtons to the right.
Now let's do the same for the verticals. We have plus 480, minus 360, and another minus 360. The total there comes out to negative 240 newtons. So all that up and down pulling boils down to one net pull downwards with a force of 240 newtons. We are so close. We took 3 complicated diagonal forces and proved they're the same as 2 incredibly simple ones, one pulling right and one pulling down. All that's left is to combine these two into our final single answer.
So this is where we've ended up. You can completely forget about those original 3 forces. The system behaves exactly as if it were being pulled by a 608 Newton force to the right and a 240 Newton force straight down. And what shape does that make? A perfect right-angled triangle.
And anytime you see a right-angled triangle and you need to find that long side, you know who to call, right? Our old friend Pythagoras. His famous theorem is the last tool we need to lock this whole thing down. So we just take 608 squared, add it to 240 squared, and then take the square root of that whole thing. And the answer, the final magnitude of the single force that does the job of all 3 originals, is 654 newtons. That's it. We found it.
And that's really the big takeaway here. That entire messy 3-way tug of war is perfectly identical to just one single rope pulling with 654 newtons of force, down and to the right. We took a chaotic system and found the simple truth hidden inside.
So, we use this divide and conquer idea to solve a pretty tricky physics problem. It kind of makes you think, doesn't it? What other complex problems in life, maybe a huge project at work or even a personal goal, could feel a whole lot less scary if we just applied that same strategy, if we just broke them down into simpler, more manageable parts? Just some food for thought. Thanks for joining me.